Hi, welcome to Concept Based. I'm John Hepworth, and this is a Year 11 extension topic. We're in permutations and combinations, and we're specifically down the bottom solving permutations and combinations problems. So today is very much a concept question that I want to do. If you know the formulas and you can just pump numbers into the formulas and you can just get answers out, then great. And if you are comfortable with that, awesome. Go ahead and do that. But what I want to try and do is explain to you today why it is that we're using those formulas that way. Because for me personally, when I was a student, again shouting out to Mr. Farduli, hello, I would always say to him, yeah, but why, sir? Why were we doing it like that? And unless I could understand why, unless I had the concept of what was going on, then I just found it hard to remember what the rule was. But once I understood why that was the rule, once I had the concept, ingrained in me, I was just like, obviously, this is the only way to answer it. So I'm going to shoot for conceptual understanding today on a very, very standard Year 11 extension question. This is highly common. It's a circular table question, and you do see these pop up regularly, and it has a restriction on it as well. So, and again, that's not uncommon either. It's a very common question. So you are seating people for an event. The circular tables have 8 seats. If at a certain table, a family of 3 must sit together, how many arrangements can the table be sat in? Okay, so first things first, circles are different. If we're lining people up and we're trying to work out how many different ways we can line people up, the order from left to right is just essentially, the number of people that there are times one less, times one less, times one less. Say if there's 8 people, you get 8 times 7 times 6, and you just go in order across there, and that helps you work out how you can go across the line. If you were doing 8 people in a line and they could be in any order, order is important. 8P8 would give us a solution for what that would be. In this one, it's circular. Now, there's a problem with circular. If we seat the person A here, B here, C here, and D here, this seating arrangement is considered identical to this seating arrangement, A, B, C, D. Now, the reason why it's considered identical is because A is still sitting beside B and D the same way A was sitting beside B and D in this situation before. It's just a rotation of that circular table, but everyone's still sitting in the same position relative to each other. So we don't consider it a new combination or a new permutation in that seating arrangement. So to remove this, what we actually do is we just anchor one person. So we have to lock one person down at the table, metaphorically, but we sort of are anchoring them. So they're anchored, so we can't move A. A is just put in a seat. We can move everyone else, but we can't move A. So back when we had those people in a line, it's like locking down a first person in the line and then doing the calculation with everybody else. If you do that, you're obviously not going to have the full complement of people included in your calculation. And so instead, if there are n people sitting at the table, the calculation ends up being subtracted by 1 in relation to all of the calculations because one person isn't moving. All of the rest of the people are moving around on the table around that person, but one person has to stay fixed so that we can have the total number of combinations. Therefore, the total number of combinations of people sitting at a table is just n minus 1 factorial, so that you can essentially do what it's standing in a line minus the one person in the same way. So n minus 1 factorial for all circular tables because we want to remove that rotation. We can move everyone else except the first person we lock in. Okay, next part. The next part, this is a terrible circle. Let's make the circle better. The next part is that we're told that a family or a group of people has to sit together on the table. What we do to make this easy for ourselves is we just assume that the group is a single identity. We just say that this is the family and we treat them as one unit on the table, and we do all the combinations of them on the table. So obviously they can sit anywhere, they're still going to sit together, but we're just treating them as one unit and moving them. So that makes our calculations possible. But the third part is at the end, you need to realize that after you've moved that unit family from one place to another, the family themselves can sit in the line that they're in. So, say in the end, the family occupies 3 seats here, then let's call them M, N, and O. They can sit in all of the combinations that 3 people could sit. So they could sit M, O, N. They could sit N, M, O, N, O, M. And what have we got left? O, M, N, and O, N, M. So you get all the combinations of them sitting in this one unit group that moves around. When we do all of our combinations or permutations, when they move around, that grouping that they create moves with them. So we have to do a multiplication at the end of that number of combinations as well. Okay, so they're the basics. That's the concept. Circles are n minus 1 factorial. If you were going to take any notes, circle is n minus 1 factorial. If you have a restriction, you treat the restriction on a circle. So on a circle, restrict, make them a single group, turn them into one unit, and move with those restrictions. And then don't forget at the end, multiply by the combinations of, or the permutations of the restrictions. Multiply by restriction, let's say. I'd probably note something like that if I had a learning log to remind myself, move the restrictions as a unit and then multiply by the number of restrictions that are there, the combinations of the restrictions. Okay, so that's the concept. So let's have a look at this actual question. There's 8 seats at the table. So therefore, the total number of combinations of ways in which we could sit people if there was no restriction would be 8 minus 1 factorial, so 7 factorial, which I don't know off the top of my head, but lucky I have a trusty calculator, and I get 5,040. Again, would you have expected that that is possible? 8 people sitting at a round table, 5,040 different ways that you can sit at that table. And that doesn't even, that's not even, having rotations in there. We've locked a person in. They're all unique in that situation. So it's massive. It's so strange that it becomes so big, but it does. Now, we aren't doing this situation of 5,040 sitting situations because we've got this family of 3 that are sitting together and we're going to treat them as a unit, right? So we're removing 3 and making them 1. So there's no longer 8 seats at the table. If we remove 3, there would be 5, but the 3 become 1, so there's 6. There's 5 individual people and then a group of the family. So when we group them together and make them 1, there is now 6 people or 6 spots. So we now are then going to apply the circle formula, which is n minus 1 factorial. So it's actually going to be 6 minus 1 factorial ways that the people could sit with the family group together in a group of 3. So now we're at 5 factorial. I probably could do that in my head. 5 4s are 20, times 3 is 60, times 2 is 120. Significantly less ways that we can sit the group of people uniquely with the 3 people sat together as a unit. But let's not forget that last step. Those 3 people that are sat there in that unit are able to sit in all of their own unique combinations. And the unique combinations that they can sit in is 3 factorial ways, because we could have, as I mentioned, M, then N, then O, M, O, N, and so on. And so you get the 6 combinations of those. And therefore, the total number of ways is not an addition. Now, if you had this in a multiple choice question, 126 would be an option for you because the paper would be trying to see, do you add them together or times them? You have to times them because every single time you move that family to a new spot, then they could sit in 6 different ways in that spot. Then you move them to the next spot. They could sit in 6 different ways in that spot. So for every spot, there's 6 different ways. So we're actually multiplying by 60. We do 120, multiplying by 60, multiplying by 6. We do 120 times 6, and we get 720 ways that we can seat that table of 8, where there is a family of 3 that is sat together, but sat together in any combination of being sat together with each other. So take those takeaways there, the circle information, n minus 1 factorial, then do your restriction, then mix up your restriction, and then you get your total. Hopefully that helps you with the conceptual understanding of doing circular seating, and that the formula makes sense. And you want the formula to make sense so that you can remember it, because understanding why helps you do that.